Okay, so the max flow min cut theorem. What I said in the last part about the value of a maximum flow is equal to the sum of the capacities across a minimum cut between S and T. So we're going to see what that means and sort of get a bit more insight into what a cut is. So the statement of the theorem, which you also get in math. So the first time I saw this was in just a math course, in a math department, no computer science involved. If F is a flow in a network, which for us is just a graph, a directed graph GVE, with edge capacities, with source S and sink T, then the following conditions are equivalent. F is a maximum flow in G, which means you can't get more stuff out of S and into T without violating these constraints that you have to obey the edge capacities, and the amount of stuff going into a vertex is equal to the amount of stuff coming out, except for S and T. The residual network there in the book is G sub F, contains no augmenting path, and the value of F is equal to the sum of the capacities across some cut ST for some cut ST of G. Okay, so here for the maximum flow we got in the, and I always forget to draw, now I don't know which of these black pens is the good one. Yes, there's this edge, which we're not using. And so this is the flow network G, okay, where we have what we think is the maximum flow, and this is the residual network, residual network, G sub F. I will write in network. So remember the, how do you draw the residual network? Well, you just consider how much stuff you could add in each direction. And if you've got something flowing in one direction, then you could sort of add that negatively in the other direction. So you think if you're shipping 7 crates of pucks from Vancouver to, is this Calgary? Calgary. Then you could, and you could ship 13, then you could increase it by 6, or you could decrease it, which is the equivalent of shipping stuff from Calgary to Vancouver. So that's why you could increase by 6 or decrease by 7. And here you could increase by 6, or you could decrease by 4, and then you could also send 4 more crates in the other direction. So that's why this is a 6 and this is an 8. Okay, so this is how you draw the residual network. And then you have the flow network. So this, I forgot to label, this is T. So S and T, S is a collection of a subset of vertices that contain S, the source. T is a subset of vertices that contain T, the sink. And the cut, so it partitions the vertices. And this cut is the, it's the edges that go from S to T, or from, and the edges between S and T. So what is it? So okay, that's a cut. Okay. So what is the capacity of the cut? Well, it is the amount of stuff. It's the sum of the unused capacities of the edges going from S to T. So here, it's nothing. Okay. There's no unused capacity. So the used capacity is 12 of this cut is 12 plus 7 plus 14 is 23. Okay. So intuitively, if you can take a cut, right, and you say the total capacity of the edges going from S to T is 23, then there is no way you can send more than 23 crates of pucks from S, from the source S to the vertex to the sink T, because there's no way you can get more than, ignore the edges going this way, there's just no way to get more than 23 unit crates of pucks across this gap. Okay? So that part is pretty clear. Remember way back at the beginning of the course, we did this thing with Eulerian tours, Eulerian cycles. And we said, okay, a graph is Eulerian if it's connected and it's all the degrees are even. If and only if, and we said, well, it's pretty obvious that this is a necessary condition, right? Because if some vertex has an odd degree, then then when you arrive and you leave, or you arrive and you leave, then you, and this is for an Eulerian cycle, not an Eulerian tour, because for an Eulerian path, you can have two of them that have odd degree. So he said, okay, well, that's obviously a necessary condition. Is it a sufficient condition? We saw that it was. Well, this is obviously, this is something like that. This is, obviously, you can't push more from S to T than the sum of the capacities across any cut, any ST cut, because you can't send, it's like if these are pipes, you can't send more than that many units of whatever through these pipes across these edges on these trucks. So it's pretty obvious that the capacity of any cut is an upper bound. So in particular, the capacity of the minimum cut is an upper bound. You can't send more than the total capacity of the minimum cut. So now we just have to show that you can send that capacity, that the maximum flow can actually reach that value. So why? Okay, so now we see the cut. So F is a maximum flow in G. Okay, suppose that F is a maximum flow in G, right? Then that means the residual, so here we're going to show, we're showing that 1 implies 2. If F is a maximum flow in G, then the residual network GF contains no augmenting path. Well, so if it is a maximum flow, then it contains no augmenting path. Well, okay, suppose GF does contain an augmenting path. Then you can add something to F. So F is not maximum. Okay, so this is like saying, remember propositional logic, which we love so much. We're trying to prove P implies Q. Well, this is equivalent to saying not Q implies not P. So we're saying if there is an augmenting path, then, so these two statements are equivalent logically, then F is not a maximum flow, because if there is an augmenting path, then we can take the value of that, the minimum capacity along that augmenting path, and add it to F. Okay, so we're done this part. 1 implies 2. Now we want to do 2 implies 3. The residual network contains no augmenting path. Well, that means that for some cut, okay, so it contains no augmenting path. So there is no way to get from S to T. So that means that at some cut, there's no way to get across the cut, right? Because if for every ST cut you could cross it, then you could actually find a path from S to T. So there is some cut, ST, such that all of these edges are going from T to S. There's no edge going from S to T. Okay, so okay, we have, if there is no augmenting path, then there is some cut like this, and then we say, okay, so the f is equal to the capacity for that cut, and that is because now if we look back in this graph, so that means that all of these edges, so remember, we don't care about this edge anymore. This is why I can keep forgetting it, because, well, I'll leave it in there, but we only care about this edge, and this edge, because they're the only ones going from S to T, okay? So these edges have to be, remember, they're not going the right, these edges, there is no edge going from S to T in the residual network. So that means that these edges are at full capacity. Because if this were 3 out of 4, then there'd be a 3 going this way and a 1 going the other way, because we could add something to it. So these edges are at full capacity. So that means, remember, these laws say that the amount of stuff flowing in has to be the amount of stuff to any vertex, is the amount of stuff flowing out. So that, where does stuff come from? It only comes from S. And we have the sum of the capacities going across these edges. And they don't come back, because otherwise we would, if they were coming back, we would be able to reverse that flow, and we would have, like, if we had 4 out of 9 coming here, then there, if this were a 4 coming this way, then in the residual network, there'd be a 4 going that way. And we don't have that. So everything is going across here. And that means it must be the flow across here, it must be coming out of S, and it must be going into T. So, okay, I hope you believe me. Oh no, so we already have, okay, that was 2 implies 3. Now we're just going to say 3 implies 1, and that is because if the flow is equal to some, so this is actually the easiest that we already discussed, if the flow is equal to the capacity of some cut, so if flow is equal to the capacity for some cut, then it has to be maximum, because you've identified this place where you can't push the capacities of the edges going from S to T. You've already filled those edges to capacity. You can't send more across. So this is the easy part. 3 implies 1. So the tricky thing, if you forget the algorithmic stuff, if you take 2 out, it's easier to still show that 3 implies 1, but then it's harder to show that 1 implies 3. So this is why we like, it's cool to use augmenting paths. Even, it's cool to know about augmenting paths even if you don't care about the algorithmic stuff. So that's the, okay, so I hope you will remember, not for the next thing, which I'm going to show you, but for the thing after that, I hope you will remember what a cut is. I mean, just remember it enough to do a question 5 on assignment 6. And maybe a question on the final exam. Probably not. Depends how mean I'm feeling. Okay, so why, apart from sending hockey pucks from Vancouver to Winnipeg, why do we care about this stuff? And the answer is, well, one, I'm going to show you a problem that easily reduces to finding max flow, which is, suppose you have two sets of things. So you have workers and machines, right? So you have some workers and you have some machines, and not every worker knows how to operate every machine. And okay, so maybe this worker is maybe this worker is useless. I don't know, but let's make this worker know how to operate some machine. Okay, like that. Okay. So now you want as many machines operated as possible under the constraint that each worker can operate only one machine. So you say, okay, is it possible for, well, okay, so the question is to select a set of edges such that no worker is trying to operate two machines, and no machine is operated by somebody who doesn't know how to use it. So basically, this question, you end up with, so this is a question of finding a maximum matching in a bipartite graph. So these two sets of vertices are the two bipartitions, and you want to find, remember we've seen matchings before when we did vertex cover, I think. And so you want to find a maximum subset of the edges such that no vertex is incident to two of the edges in the subset. Okay, so how do you do that? Well, you can turn this into a maximum flow problem where you say, okay, everybody, I put a vertex S here, and I put a vertex T here. And I put, okay, every worker can operate one machine, and every machine can only be operated by one worker. And then these weights in the middle can be infinite, I think. And so this is nice because if you do the Ford-Fulkerson augmenting path thing, then if you have integer capacities, you end up with an integer flow. So the flow across every edge is going to be an integer, which means that everything is either 1 or 0. And then, so if you have, and also the flow across all of these edges is going to be 1 or 0, and so you can't have every worker gets inflow 1 if you have gets inflow either 1 or 0 and goes to exactly one machine. It doesn't split. So that's easy. So you can solve this problem by reducing it to maximum flow and then doing Ford-Fulkerson. So that's probably the easiest problem, easiest reduction to a max flow to this. So. Okay, technically we saw divide and conquer, greedy algorithms, dynamic programming, and we said these are, and then we saw graph algorithms, but the graph algorithms were basically generally broke down into either being greedy, like minimum spanning trees, or or Dijkstra's algorithm is sort of greedy and sort of dynamic. I think it's probably more dynamic. So network flows are another paradigm which we don't really have time to cover in detail. There are other ways of other tools, other weapons in the arsenal. Linear programming is a big one, which I don't know if Norbert gets to it in like algorithms too, but in third-year algorithms, generally no. Maybe in a couple of places. Now, if I have time, maybe we're going to talk about, I'm going to pause it. We're going to talk about a more interesting reduction to network flow from the textbook. But I'm going to pause it so that I can write this question